Hi, folks. So we are back at it with Module 5 notes, and there are three major sections in this module. The first section is basic probability, and then we move on to probability distribution functions, and specifically we're going to then move on to the normal distribution, which is a PDF, a probability distribution, and we're going to also talk about the binomial distribution, which is also a PDF. So probability is just the study of randomness. Chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. For example, if I flip a coin 2 times, I expect 50% of the times I flip a coin to be heads, but I don't expect to get one head and one tail every single time when I flip a coin twice. But if I do that over and over and over again, I do expect it to be about 50% heads. The probability of any outcome of a random phenomenon is the proportion of times that outcome would occur if an infinite series of repetition. Probability describes what happens in the long run. And probability is the basis of statistical inference. So early on in the semester, I told you we had descriptive statistics. That was the first type of statistic we were going to do. Then we had probability, and then we have inference. We are now in this part of the statistics class. So we finished with descriptive statistics, which is how to display and describe numerically our variables. Now we're in the probability, which is sort of the backbone for inference, which is where we're going next. Okay, so let's look at our first example. Suppose that I teach a class containing 30 students. 12 of the students are neuroscience majors and 18 are other majors. What is the chance or the probability that a selected student will be a neuroscience major? The probability of being a neuro major is the number of neuro majors in the class over the total number of people in the class. That's 12 over 30. If I change that to a decimal, it's 0.4, and if I change that to a percentage, it's 40%. This is considered theoretical probability. It's what would happen in theory based on the numbers in the class. Here's another example. In a recent Gallup poll from May 2017, a random sample of 1,011 adults living in the United States revealed that 192 of them felt that the statement, human beings have developed over millions of years from less advanced forms of life, but God had no part in this process, most accurately reflected their views. What proportion of adults in the United States agree with this statement? So in this one, the probability of people who agree with the statement is F over N. Remember, F is a relative frequency when it's put over N. The number of people who agree with the statement is 192, and the total number of people in the sample is 1,011. That's approximately 0.9 or 19%. And when we use a sample to say something about probability, we often put an apostrophe on this probability statement. Not everybody does it. You don't have to do it. This is experimental probability. So in the first example, we were saying what would happen in theory if we did this over and over and over again. And in the second example, we're using a sample to tell us what the probability is. Random samples eliminate bias from the act of choosing a sample, but variability will always exist, and because of this, a sample may be inaccurate. We can get a bad sample just by chance. So ways of assigning probabilities. The first way is subjective probability. That's an expert opinion. By the way, it's typically the worst kind. Classical or theoretical probability uses a sample space. It assumes equally likely outcomes and it's based on reasoning. And then empirical or experimental probability, we repeat an experiment a large number of times or take a large enough sample and observe what happens. Sampling or repeating an experiment is what we're talking about there. Sometimes, by the way, this classical or theoretical probability, you'll see me call it the true probability. I just use that word, it's shorter. Um, so in the classical or true probability, we're looking for the probability of some event E. And then in the experimental probability, we're looking for the probability of some event E, but we may use this apostrophe in this notation. By the way, that notation is often ignored, so don't worry about it if you don't see it or if you don't want to use it, it's okay. So let's look at an example. What's the probability of getting heads when we flip a coin? Well, we all know that it's 50%, or 1 out of 2, 1/2, or 0.5. If I flip a coin 2 times, will I get 1 head and 1 tail for sure? Certainly not. It might happen, but it might not. If I flip a coin 10 times, will I get exactly 5 heads and 5 tails? Certainly not necessarily. So in both of these cases, this is not necessarily. Could happen, may not happen. What'll happen though if I flip a coin many, many, many times, like 5,000 times? Well, if we look at this graph is an example of what happens when we flip a coin once. In one of these examples, first of all, we got 0 heads the first time. Whoops. We got 0 heads the first time, so the probability of heads was 0. Then the second flip, I got heads, and so the probability of heads is 50%. And then I continued to flip over and over and over again. And what you see with this blue line is that it's stabilizing at 50% heads. This number here is my theoretical chance of getting heads. It's 50% or 0.5. In the other example, we got a head the first time, and so the chance of getting heads was 1. And then I continued to get heads 5 times in a row. So the chance of getting heads was still 1 or 100%. And then finally, I started getting some tails, and then finally, I got some more tails, and eventually it calmed down. And when we look, by the time we get out to a couple hundred or a couple thousand flips of the coin, this graph stabilizes. So the graph stabilizes as sample size, or the number of times we do the experiment, increases. And it stabilizes right at that theoretical probability. This is a visualization of something called the law of large numbers. As the number of repetitions in an experiment increases, the proportion with which a certain outcome is observed gets closer to the actual or classical probability of that outcome. So the experimental probability of event E, that's the experimental, approaches the theoretical or true as n approaches infinity. Now we have some vocabulary for this unit that you'll need to be familiar with because I'll use it. The first one is in a probability experiment. You've already seen me do this. It's a repeatable process where the results are uncertain. An outcome is the result of a single trial of a probability experiment. A sample space is a set of all possible outcomes of a probability experiment, and we usually denote it with S, but you could use any example, any letter. And our first example is if we roll a fair die, the sample space S is, and we use braces to denote this, 1, 2, 3, 4, 5, 6. And if we were in a live class, most of the time somebody would tell me it's 1 to 6. You do have to be cautious though, because this is discrete. So, well, we all know what you mean. Make sure they understand no fractions or decimals are allowed here. The next example, the temperature in my office on any workday, the sample space could be anything from about 62 degrees Fahrenheit up to about 92 degrees Fahrenheit because I'm in a really old building. And this is continuous. And whether we have discrete or continuous data is going to be important in a few minutes as to how we represent that data. An event is an outcome or a set of outcomes of a probability experiment. Examples of events when we roll a fair die could be rolling a 1. The event could be any odd number, and then the event could be anything 4 or more. All of these things are all events. Probability rules govern the math on how things behave. A probability can be assigned to each outcome or event in a sample space. This probability is a number between 0 and 1 in fraction, decimal, or percent form. So the probability of some event E is between 0 and 1, or if we use percentages, it's 0% up to 100%. And let me put a percent after that 0. So we can use decimal, fraction, or percent form. Probabilities closer to 1 indicate that the event is more likely to occur. An event with probability of 1 must occur. Probabilities closer to 0 indicate that the event is less likely to occur. An event with probability 0 cannot or will not occur. Complement, and this is not you look pretty today, it means the opposite of. The complement of an event is its mathematical opposite. And complement you look pretty today is spelled with an I in the middle of the word. This one is spelled with an E. The complement notation, there are lots and lots of different notations depending on whether you're doing philosophy or math or statistics or computer science. So here are all of the ones that I know about. The first one is not A. The second one is A prime. The third one is A with a C as an exponent. And the next one is A with a line all over it. All of these are notation for complement. The probability of event A plus its complement must add up to 1. And that's if you look over here on the left. When we talk about the sample space, something is either event A or it's not event A. And so it's either in the yellow circle or it's in the pink, and the chance of both of these things happening has to be 1 or 100%. So if we know the probability of A, we also know the probability of not A. So the probability of not A is equal to 1 minus the probability of A. And that's what that notation there, probability of A prime, is equal to 1 minus probability of A means. So let's use this in an example. A recent nationwide study of myopia, which is nearsightedness, found that 38.1% of Americans aged 18 to 24 suffer from myopia. The probability that a randomly chosen American between the ages of 18, 20, and 24 does not have myopia, well, if the probability of myopia, and I'm going to use M because myopia starts with an M, is equal to 0.381. We typically use decimals or fractions to do this math. So the probability of not M is equal to 1 minus the probability of M. It really is that simple. So it's just 1 minus 0.381. Whoops, I don't need a parentheses there. And that's equal to 0.619. So if I know the probability of M, I can calculate the probability of it not happening or not M by just doing 1 minus that number. So 61.9% of people in the 18 to 24 age group do not have myopia. The next thing we want to talk about are independent and dependent events. Let event A equal drawing a 5 from a 52 card deck, and event B equal drawing a 5 from the same 52 card deck. So for those of you that aren't familiar with cards, I've got a picture of them here. There are 52 cards. The first row has black cards in it, and they have a picture here that looks like a 3-leaf clover. Those are called clubs. The next row has red cards, and those have diamonds on them, so they're called diamonds. The next row has cards that have hearts on them, and the last row is black cards again, and this has spades on them. This spade sort of looks like an upside down heart. In every suit, there are 13 cards total. One of them is an ace. It sort of represents a 1 up to 10. And then 3 face cards, the jack, the queen, and the king. So what is the probability of event A? Well, what we want to know is event A is drawing a 5 from our 52 card deck. So what's the probability of event A? For us, that's the probability of drawing a 5. So I'm just going to write probability of 5 there. So it's the number of 5s in the deck over the total number of cards in the deck. Well, let's look at this. I'm going to use dark green here. Here are the 5s. There are 4 of them. And there are 52 cards, so it's 4 out of 52. And that is approximately 0.077. By the way, 4 out of 52 is 1/13th, but we do not reduce our fractions when we're doing probability because this denominator actually has meaning. It tells us how many items are in our sample. So now let's look at if you drew a 5 on the first draw, so event A occurred, and you don't replace the card, then what's event B? So let's say we got a 5 of clubs and we didn't put it back. So we get rid of that card, and now we have this new sample space. This new sample space, probability of B, is equal to the probability of getting a 5 when we got a 5 the first time and didn't put it back. Well, now it's the number of 5s we have now and the total in the deck we have now. Well, we got rid of 1 5, so there are only 3 of them. And we got rid of 1 card, so there are only 51 cards, and that's approximately 0.059. So notice, if we do not replace the card, it changes the likelihood of this event happening. If you didn't draw a 5 on the first draw, if event A didn't occur and you don't replace the card, then what is event B? Well, in this case, I'm going to get rid of my crossing out. Let's say, I'm going to use pink here. Let's say I drew a 7. So if you didn't draw a 5, so let's say I drew a 7, well, the probability of getting B, which is the probability of 5, when I didn't draw a 5 the first time, it's still the number of 5s now over the new total, the number in the total now. Well, I still have 4 5s because I didn't get one the first time. So there are 4 of them. But I got a 7 and I didn't put it back. So there are only 51 cards. So it's 4 out of 51, which is approximately 0.078. And then finally, if you don't replace the first card drawn, are events A and B independent or dependent? They are dependent because the first event affects the second event. And then I'm going to go do red here. If you do replace the first card, in other words, you put it back, are events A and B independent or dependent? They're independent because BC, the odds stay the same. So two events are independent if the odds don't change, and two events are dependent if the odds do change. Regardless of whether event A occurred or not, if you don't replace the first card, these two draws, events A and B, are not independent. The probability of event B occurring does change depending on whether or not event A occurred. They are dependent events. Conditional probability. When calculating the probability for dependent events, we call this conditional probability. Conditional probability is the chance of B occurring given the outcome in A. The notation is B vertical line A, where this line here means given or on this condition. Hence conditional probability. So this notation here, probability of B given A, is equal to the probability of A and B divided by the probability of A. If the probability of B given A is equal to the probability of B, then we say that A and B are independent. And if two events are independent, then the probability of A times the probability of B is equal to the probability of A and B. All right, multiplication rule. The probability of A and B, which is also the probability of A upside down U, this thing means intersection of B, the probability that in one statistical trial, both events A and B occur. If A and B are dependent, the probability of A and B is equal to the probability of A times the probability of B given A, and vice versa. The probability of B is equal to the probability of A given B. So if we have dependent events, what that means is that we have overlapping Venn diagram circles. So event A is in circle 1, event B is in circle 2, and these two events overlap. And when that happens, one event can or will affect the other. This overlap is our probability of A and B. If A and B are independent events, then the probability of A and B is equal to the probability of A times the probability of B, and the probability of A and B is equal to the probability of B times the probability of A. Mutually exclusive or disjoint events are not the same. They're actually the opposite of independence. Independent explores how probabilities are changed when two or more events occur in one statistical trial. Events A and B are mutually exclusive or disjoint if they cannot occur simultaneously. So these two events here, where A and B are separated from one another, are mutually exclusive, and specifically they are disjoint events. It means there is no overlap. All right, so now let's get into some of the math. The addition rule. The general addition rule for any two events. This rule works if the events A and B are joined or if they're disjoint. So for any two events, A and B, the probability of A or B is equal to the probability of A plus B minus the probability of A and B. The notation for probability of A or B is the probability of A union B, where we use the correct shape U. It's in the right direction. U stands for union mathematically. The addition rule for disjoint events is the same thing. It's the probability of A union B is equal to probability of A or B is equal to this same thing up here, probability of A plus the probability of B minus the probability of A and B. But because we have disjoint events, the probability of A and B occurring at the same time is 0. And so that falls out of the equation, and that's why our equation doesn't have that part in it. All right, so I've gone through a whole lot of theory and a whole lot of equations, but how do we apply these things? Most of the time, there's a lot of logic applied here and students get it, but there are a couple of times where this is a struggle for students, and I'm going to point those out. So we're going to use a contingency table. The table shows the results of a study of U.S. children in which researchers examined a child's IQ in the presence of a specific gene. This is from psychological science. So if a child in the United States is selected, what is the probability that the child has the gene? So we just want the probability of the gene. Well, I look for the column or the row that has the gene in it. There are 72 kids with the gene, so it's the number of people that have that gene over the total. It's just a relative frequency. Pretty much everybody would have been able to calculate this. It's 72 divided by our total, which is 102. And if we make that a decimal, it's 0.706, or we can have it as a percent, which is 70.6%. Remember, for probabilities, we can use fractions, decimals, or percent. Next example, and I'm going to erase my marks on the contingency table. What is the probability that a child does not have a normal IQ? So does not have a normal IQ. Probability of not normal removes everybody who is normal. So that is 1 minus the probability of normal. This is the complement. So it's 1 minus, there are 50 kids who are normal over 102. And if you do the math there, you get 0.51 or 51%. Approximately. All right, so then the next one, C, is compute the probability that the child has no gene and a normal IQ. So the probability that they have no gene and normal IQ. Probability of no gene and the normal IQ. Well, the probability of no gene and normal IQ is where these two things overlap. So let me erase my marks on my contingency table. The no gene group is in the second column. There are 30 of those. And the normal IQ group is in the second row, and there are 50 of those. And the place where those overlap has 11 children in it. And so there are 11 children that have both no gene and the normal IQ over 102, and that is approximately 0.108 or 10.8%. So once again, we're just reading off of this contingency table for the scenario we have. So far, common sense and basic reading of this contingency table, most of you would have gotten all of these so far. The next one is a little bit weird. People tend to struggle with this one. Find the probability that a child has no gene or normal IQ. So the probability of no gene or, this is important, a normal IQ is equal to, and remember this or rule back here, for any events for ors, we have to take off the and that's because of an overlap. So in our case, it's the probability of no gene plus the probability of normal IQ. And I want to show you what's happening before I write down the rest of the formula. So I'm going to erase everything on the contingency table. So the kids that have no gene are in the second column. There are 30 of those. And then the normal IQ kids are in the second row, and there are 50 of those. But when we're talking about the OR group, we are counting the 19, the 11, the 39, and then we counted this 11 again. And that's why we have to subtract off the probability of no gene and normal. It's because we counted those 11 kids twice. So probability of no gene, there are 30 of those kids, so it's 30 over 102. Probability of normal, there are 50 of those kids over 102. But remember, we counted those 11 kids where it overlapped twice, so we just have to subtract that off. And that's equal to 69 over 102, and that's approximately 0.67 or 67%. By the way, it's 69 over 102, which is approximately 0.676, sorry, which is approximately 67.6%. All right, there are other ways to solve this particular problem, and if you see the other way, it will always work. And then finally, the last one is, what is the probability that a child has a normal IQ given on the condition that the child has no gene? So the probability of a child having normal IQ given, that's that vertical line, that the child does not have the gene. Well, let's go back and find the formula for that. Way back on page, I don't know, page 4. Oops. So the conditional formula is here. Probability of B given A is the probability of A and B divided by whatever was given. So it's the condition, it's the second thing that occurs. And so in our case, we have the probability of normal and no gene divided by whatever happens second has to be in the denominator here. So it's the probability of no gene. So let's go back up and look at our table again. Again, I'm going to erase all my notes. So we want the probability of normal and no gene. So normal and no gene is where those two things overlap. So that's 11 out of 102 divided by the probability of no gene. And no gene, there are 30 of those out of 102. And that is 11 out of 30. By the way, if you see the other way to do this and automatically looked at the table and thought, oh, it's just 11 out of 30, your method will always work and you can use that method. 11 out of 30 is approximately 0.367 or 36.7%.